In this video, we will discuss some greedy algorithms and we'll see how it can be very useful to solve a certain set of problems, but at the same time it can be very deceiving and it can convince you that your solution is correct when it in fact has a counterexample. Let's start with the problem. You are given an array that contains an integer. Suppose those integers are 2, 3, 1, 9, 0, and you have to construct two different arrays out of it. One is the prefix min, and the next array that you have to construct is prefix max. So the prefix minima would just be 2, 2, 1, 1 and 0, and the prefix maxima would be 2, 3, 3, 9 and 9. Once you have constructed these two arrays uniquely, you have to construct a third array where you get a choice for each of the elements. That is, for when you want to add an element over here, you have a choice to independently pick one element from the prefix minima section or the prefix maxima section for that particular index, and then you can repeat the same thing for the other indices as well. So you can see that there are 2 to the power n possible choices to create this array. Now your goal is to maximize the number of inversions that you can have in the array that you create. Overall, to the power n configurations of the resulting array, you have to print the maximum number of inversions that you can have in a single array by still following the rules. And the rules are, for each index you either select prefix minima or prefix maxima. No other constraints are there, and you can assume that all the elements that are given to you, they are unique, but you can still solve the problem even if they are not unique. Now, before we approach this problem, let's talk about the strategy to compute inversion, and let's make some notations clear. If you have this particular array, and let's say if you have an element a1 over here and an element a of x over here, how do you count the total number of inversions? And I'm not looking for an optimal answer over here. I just want the correct strategy. So to do that, you can say that element a of x, how much will it contribute to the inversion count? So you only look at to the left. An element can only be inverted with an element to its left, not to its right. So you might wonder that, oh, why are we adding this artificial constraint that this element will only be inverted with an element to its left? Because we want to avoid double counting. Because if you want to say that this is inverted with this as well as this, but then when you are using the contribution, so you added this contribution for both of these curved lines when you are at this element a of x, but when you arrive at a of y, you will add this line again, right? So this line will be repeated. So that's why for problems like this, we enforce an artificial constraint then that an element will contribute the number of inversions by comparing it only to the left hand side, not to the right hand side. So in this manner, you can see that this element, right? And suppose that this element is 9, then if there is any element that is greater than 9 on the left hand side, then that element and this element will be inverted, right? Because inversion denotes how far are you away from sorting the array, because a sorted array has inversion count as 0, right? Sorted means 0 inversion, and from there you can visualize that if all the elements are in increasing order, like let's say 1 2 5 9 7, this array has 0 inversions. Okay, so now you can conclude that for any, and that is in fact the definition of an inversion, right? So nothing new here. Inversion basically says that I is less than j, but their values flip. Ai is greater than aj. This is the definition of aj. This is the definition of inversion. We are just adding an additional constraint that for each element we will, while while calculating the contribution of this elements to the inversion count, we will only look at elements to the left. So now you can see that the sorted array has the maximum number of the minimum number of inversions, which is 0, but the reverse sorted array, sorry, the reverse sorted array, that will have the maximum number of inversions. And why is that true? Because the highest element you have placed over here, so this will not be inverted with anything because we are only looking at the left, that's fine. Then the next highest is located over here, so it will be inverted with everything that comes to its left. Then the next uh, the highest element is placed over here, and the second highest element is placed over here, the third highest element is placed over here. So you can see that for when you keep an array in a reverse sorted order, if you have this array, if you keep this in a reverse sorted order, then each element I will be inverted to all of its neighbors on the left hand side. So the maximum number of inversions that you can get will be equal to the summation of I, which is n into n minus 1 by 2. So now that you know this fact, and you might have already known this fact, that the maximum number of inversion comes from a reverse sorted array, then coming back to this original problem, right? For this particular problem, I don't want you to find a very optimized solution or anything, just that the solution has to be correct. So even if you give me an n to the power 5 solution, I'd be content with it as long as it is not exponential is in nature, right? We are just looking for the correctness in this particular video. So think about it, like at any point of time, prefix maxima, right? Prefix maxima of I, maxima is always greater than a minima, right? So prefix maxima of I is always greater than or equal to prefix minima of I. So if you are given the choice, on do you want to add the maxima or minima in the first element, what should you go with? So of course you would want the highest elements first, right? So that uh, all the lower elements, like all the lower elements that are on the end of the segment, they start creating inversions with everything that is on their left hand side, right? So you can see that in an ideal split, right, you might want, let's say, half prefix maxima, in n by 2, and prefix minima in n by 2, right? And then you might think that this might create a good set of inversions, right? And this is in fact the first greedy approach that comes in mind, like divide it in half and half so that everyone gets equal contribution, and then you kind of maximize the number of inversions. But of course, like some of you might already know that this argument might not work, and even though you might feel like, if you are a beginner to competitive programming, you might feel like dividing half and half is good, but that might not be the ideal strategy. So if you are a little bit experienced but not a pro in competitive programming, you might think that, okay, this is the obvious greedy solution that is wrong, and the correct solution that explores all possibilities is this, that you divide this prefix maxima. Like nobody is guaranteeing that half and half is the best split, right? So some of you skeptics might think that, okay, the best strategy is to explore all possible options, which is you have a block, k blocks of prefix maxima, and the remaining n blocks of n minus k blocks of prefix minima, right? N minus k minimas and k maximas, right? And then you might convince yourself that, okay, you if you iterate over all k, where k goes from 0 to n, right, then you have already considered all the possibility, and then if you take the maximum value of across all of these k's, right, maximum across all k's, then you can have your answer, right? So this approach is the one that you might most likely come up with, if you are like, let's say, rated around 17 or 1800 or so. And in fact, this approach is kind of correct, but and it might pass a lot of test cases as well. But I'll tell you right away that in fact, this greedy strategy that you are smartly thinking is correct, like varying k over all these segment sizes, that is also incorrect. And maybe try to pause this video and come up with a counter example that proves that even if you even if you have some even if you iterate k over all of these sizes, even then you might miss some possibilities. And in fact, dividing max and then all the prefix minimas is not the optimal strategy. So try to pause this video and come up with a counter example, because this is a bit tricky to find, and that is the reason why I'm creating this video in the first place. In fact, I myself was so confused on this, like I couldn't even believe that this strategy with k is not correct, right? So I spent a good deal trying to figure out what the counter example could be. And then finally, when I saw the solution, I was pretty convinced that yes, this approach is indeed incorrect, right? So that is what happens with greedy problems. Like uh, you have to see, first of all, you have to not be scared of thinking about greedy strategies. But then, if your greedy strategy does not work, you have to be comfortable with proving why it does not work or finding a counter example. So here is the counter example for that greedy strategy that we just discussed. Suppose the original array is 5, 4, 1, 2, 3, 6. Now you compute the prefix minima. Prefix minima would be 5 and then 4, then 1, 1, 1 and 1. Then you compute the prefix maxima. So it should be 5, 5, 5, 5, 5, and then here it will be 6. Then the optimal uh, distribution you can try with, so this is the prefix maxima, right? We have written max over here and we have written min over here. So you can try by hand all the possibility where you take a prefix from here and a suffix from here, and you will see that the maximum you can reach is 9. But if you consider this array where you take, so here it is 5 and 5, so it's equal, doesn't matter. And then you now switch to the minima, but now you come back to the maxima, and then now you keep the minima as it is. So you will see that this one produces a total of 10 inversions. Why does it produce 10 inversion? Because 4 is inverted with 5, this is one inversion, and 5 is inverted with nothing, so this is 1, and then 1 is inverted with all three elements, right? So it is 3 into 3 plus 1, right? So you are getting 10. But in all the other scenarios, you can try and you can see that you are getting 9. So how did I even come up with this counterexample, right? And if you now know this counterexample, then you can convince yourself that okay, maybe your gut feeling said that you should have all these prefix maxima first and then the prefix minima. But then I just showed you that maybe alternating them was a better choice, right? So maybe your gut feeling is not always right, or is it? We'll see later in this video. So we know that we have some gut feeling that okay, maxima should have been before minima, but and we were pretty convinced that it was correct, right? But then there is only a few set of counter examples where it is failing. So maybe these set of counter examples itself are very specific, because if you remember, I recently uploaded a video on a code forces problem. I think it was around problem E or F in a code forces round. And there we discussed about why a greedy strategy that looks incorrect at first, it can actually be modified to be correct, right? And that problem was about certain fractions, right? It was about increasing the numerator by 1 or decreasing the denominator by 1. So you can also watch that video. That also has a lot of good insights on dynamic on greedy problems. Okay. So maybe we can utilize this insight as well. Like we have some gut feeling that okay, some prefix should be the maxima and then some suffix should be the minima, but this is not working out of the box, so maybe some modifications are needed. But what exactly we'll see. So now we have our first lesson that okay, sometime gut feelings helps but sometime it doesn't, right? So when it doesn't, we should go back to the drawing board and start thinking about the problem in a way that we can prove, right? So if you have this array, what is one thing you can say for sure? One thing, one element that you can guarantee for sure is the last element, right? Because let's consider this last element. Now in this last element, you have a choice. You can either place a minima over here or you can place a maxima over here, right? Now you can see that this is the last element, right? So, and we have already decided that one element only inverts with the neighbors on the left hand side, not on the right hand side. So since there is no element on the right hand side, so no matter what choice you make for this particular element, only this element's contribution will be affected. All of these elements will not be affected. So given the choice, would you like to place the maximum value over here and make the array almost sorted, or would you like to place the minimum value over here? So of course you would want to place the minimum value over here, right? Yeah, instead of keeping like let's say 5, you might want to keep something like 1. Why? Because 1 gives you a better chance of being inverted with everything. But even if it is not, then it still, like, you had better chances, right? So you would definitely want 1, basically the prefix minima, to be placed over here, right? Now you can apply that same reasoning by trimming down the size by 1, right? And then you can apply that same reasoning over here. Like, what is the element that you would like over here? Would you like a prefix maxima or a minima? Then you can see that of course you would always want a prefix minima, right? So you can continue this logic over here till here, and then you realize that this algorithm is basically saying take prefix minima at every stage, right? And in the previous slide, we were discussing an algorithm that told us to take some prefix maxima and then some prefix minima. So what is actually wrong with our analysis? Like, how come we applied the same logic that is of course correct, right? But how come we are getting prefix minima for all the elements? And if you think about it, this prefix minima thing is actually correct, but for a very specific scenario, right? There is some detail that we are missing, and the detail is that if I give you n unique elements, right? If I give you n unique elements, then yes, definitely at every point from right to left, you would always want a prefix minima, right? If all the prefix minima are unique, right? So see, doesn't mean that if you have n unique elements, you will have all unique prefix minima. But if you did had unique prefix minima at each stage, then yes, you would have definitely like to pick the unique prefix minimas at each stage. So now you can already see that the one major thing that we are missing was the duplicates, right? We thought that we could get away by simply solving it for a general case, and then duplicates can be handled later on. But turns out that this problem is based entirely around duplicates. So you also now have to consider all the duplicates when coming up with an analysis. So now what we'll do is let's so you can see that we are only interested in prefix minima, never the prefix maxima, right? And our algorithm only kind of uh, breaks if there are presence of duplicates, right? So now let's consider the prefix minima array. You have this prefix minima array, and these can contain a lot of duplicates because minima might not change for a long time until you see a smaller element. So suppose this is one block of equal elements that you are seeing, then you might see an even smaller element, then you might see an even smaller element for, like, let's say lesser frequency, and then finally you see the smallest element. Okay, Now let's talk about one element over here. The last element we have already concluded that that should be the minima, right? No doubt about that. But we kind of did a hand waving argument and we said that the last second element should also be a prefix minima. But is that really correct? Because if you see, if this is the last element, okay, if this is the second last element, then it can only have inversions on its left hand side. That part we already concluded. Now it can either have the inversions with the elements that are colored white, basically those are same valued as this, or those are in different blocks, right, of or different colors. Then you can see that this minima has already changed colors, means it has already changed values, it means it has decreased. So this means that this element over here, this element x, this is definitely smaller than everything that is colored over here. Like x is definitely smaller than green or red or blue. So if you select the prefix minima over here, you will definitely, how much contribution can you get? You will definitely get the total size of all the colored elements on the left hand side, right? But what are you missing out on? You are missing out on, and this is the biggest piece, this is actually the crux of the algorithm, so pay attention. So you had this white box, so you are actually not taking advantage of the fact that if you decide to set it as x and x, and everything is x over here, every prefix minima is x over here, you are missing out on the fact that you are not inverting with the elements that are in your block. So what if you made some compromise and you said that, okay, instead of this x, I might want to go prefix maxima, or like let's say become y, and then I'll see whether I still invert with all the elements of these, or I can get some better contribution from the elements that are in my box. So now if you look at an individual box in isolation, and let me make the picture a bit more clear to you. Suppose you have this red block where you have all the prefix minima that is colored in red, basically they share all the same value. Then you have the blue block over here with all the prefix minima of the same color. Then suppose you have the green block with all the minimas, and of course all of these will be in a strictly decreasing order, right, because it's a series of minima, right? Then suppose you have a yellow block over here, and the last and the most important block that we are solving for is the white one, right? So suppose I make it very big and it has a bunch of elements that are colored white, meaning all their prefix minimas are equal in this section. Now you know that the if you stick with your trivial strategy, which is selecting prefix minima at every location, that also gives you decent profit, because if you pick any element x over here, right, since this is the prefix minima, it will always be inverted with all the elements over here, right? All the elements outside of this box, it will always be inverted, right? Because the minima has changed colors, means minima has decreased. So this element is actually smaller than this and this, right? So it will definitely get inverted with everything, right? So no matter, so even if you end up selecting everything as x over here, prefix minima, then it will be inverted with every block that you see on the left hand side. But the one thing that you are missing out on is the that this, if you set all of them to x, then this white block is not increasing the inversion count amongst itself, right? So now suppose that instead of setting this as x, which is the prefix minima, I set one particular value to the to, like let's say m, right, which this is the prefix maxima, right? Now if this is the prefix maxima, right, and remember that prefix maxima means the maximum value of the entire segment. So if you set this as a prefix maxima, then previously you were getting contribution from all of these colored blocks on the left hand side, but as soon as you set it to maxima, you would have to give those entire thing away. And for what? Only to get some bit of contribution over from here, right? So in this picture, it might seem that, okay, you should never lose this much contribution just for the sake of 4 to 5 contribution from here. But if you keep on adding more blocks, more colored blocks, you can easily see that sometimes you might have to do some trade-off to give up some of these colored boxes from over here and select it as prefix minima maxima, so that you don't take any contribution from here, you only take the contribution from inside your block, right? So the key idea is this: if you select prefix minima, if you select prefix minima of I, you will only gain contribution from outside your block, right? From outside your block. Why? Because this minima is of course smaller than everything that is greater but to its left. But if you select prefix maxima, you have to give up this entire thing, right? So if you select prefix maxima of I, then you can only gain contribution from your block, right? Only gain contribution from your block, and not just your block, only the left hand side elements of your block. Only gain contribution from LHS of your block, from LHS of your block. Now maybe for one element it might not matter, but then if you sum them up over all of these elements in the white block, then maybe that might make a difference, right? Now it makes sense to think about how to solve this problem in a particular block, right? Because we know that at the last element of the block has to be a min for sure. But how do you solve this problem for any particular block if you fix that, right? And by the way, we also have to check if the last element indeed has to be the min of that block. We'll come to that soon. So how do we solve this problem for a single box? That is, this is the series of prefix minima which is decreasing in nature. So every time the color changes, you know that the minima decreases. Now you have to decide in one box how many times will you select prefix minima and how many times will you select prefix maxima. And here actually your gut feeling, if your gut feeling again says that you have to distribute with some maximas at the start and some minima at the end, this time it's actually correct. This time you do have to have some maxima at the start and some and the rest minima at the end. Okay, and how much, like of course it won't be half and half, but how much exactly, that part we yet have to figure out. Of course, one possible way is to explore all the possible switch points, basically all the possible partition point after which you can transition the maxima to the minima, but we'll talk about that later. But first let's see why that maxima followed by a minima strategy is correct over here, but our gut feeling was not correct at that time, and why should now it be correct, right? So now let me actually show you the proof for this, right? So the proof is visual, right? Suppose you had selected minima over here, right? Suppose you had selected minima, then we know that it will not get any contribution from its own box, because all the values you might select as minima. If you are selecting all the values as minima, right? But if you are selecting some of these values are as maxima, then that's a different deal. But it will definitely get all the contribution from here, right? Because since this is the prefix minima, then it is greater than everything, right? So it will get this entire box and nothing from here. But now if you select maxima, you can clearly see that it will not get anything from its left hand side no matter what you do. Why? Because this is the maximum element which is at the end of the array. This means that this element is in its correct position if you think about sorting the array, right? This element is in its correct position in the sorted prefix. So this means that switching it to a maxima, I sets its benefit to 0 immediately, right? No benefit to this element at all. So why should you even switch to it? You should switch to it because if you set this to a maxima over here, even though this element now starts contributing 0 because there is nothing to invert against on its left hand side, it might open the doors for the elements that are on the right hand side to get some additional contribution from within its boxes. That is, if you set a prefix maxima over here and then a prefix minima over here, so this minima will still keep on getting the contribution that it used to get outside the box, but now it is also getting some contribution from inside the box. So, of course, you can see that in order to get the maximum contribution, it should be placed as far from this maxima as possible. So, ideally, you should move this towards the end. And then, when you set an element to its prefix maxima, you essentially reduce its contribution to 0. So, you would like to avoid this as much as you can, and you would like to separate out the maxima and minima as much further as you can, right? So, that's why it is ideal to have a set of prefix maxima then followed by a set of prefix minima. So this proof was very visual, but if you want a more strong like proof, you can also think something like this. Okay, you have an element x over here, and then you have some elements in between, and you have an element y now, and then some elements over here and some elements over here. And suppose this is the box, right? And I will show you why it will always be all maximas clubbed together and then all minimas clubbed together. Why cannot it be maxima followed by minima, just like the counter example that we saw earlier, right? Like, why is that counter example not applicable over here? So suppose this is the max. So suppose this is the minima on the left hand side and this is the maxima on the right hand side, right? So I have changed this order and now I'm saying this that in one block maxima can occur on the right hand side. Now let's see if we can improve the answer by swapping out these two. Okay, so first of all, let's look at this contribution of this maxima. So we know that a prefix maxima contributes literally nothing. Why? Because this is the maxima, right? So it is inverted with nothing at all. So why would you ever pick prefix maxima unless some other element is benefiting out of it? So this element is literally contributing nothing right now. So if you swap it to the left, how much will it contribute, right? So if you swap it to the left over here, so if you move it to the left, then let's focus on these segments, this segment, this segment, and this segment. Then you can notice that an element only inverts with its left neighbor, right? And so this segment, right, they can never invert with the max element that you have just swapped, right? And these set of elements, right, these set of elements, they don't care whether max is available over here or available over here as long as it is present on the left hand side. So we know that the contribution of these segments will not change, only the contribution of these segments might change. And how can they change? They can only improve. Why? Because you have moved a bigger value to the left hand side. So these elements might start contributing more, right? Because if these elements are indeed prefix minima, or even if they were prefix maxima, they might start contributing more because you did that swap, right? Similarly for this min, right? If you have this min over here, so how much is this prefix minima contributing, right? So this prefix minima, it might possibly have some contribution on this block, but even if you swap it out to over here, then this contributions, it does not change, right? The only thing that might change is from the middle block, right? The nested block. So if you move a smaller element to the end, right, there is a higher chance that this smaller element that you just moved over here, this now starts inverting with these elements in between, right? So now this was the complete proof of why swapping max with min, right, is always beneficial. That is, you should always have max on the left hand side and min on the right hand side. And we saw two kinds of, like, one is proper proof and other is visual proof, that for max you are literally taking all the blame on yourself and you're saying that, okay, I will contribute zero, but then I will open up the doors for other people. But if they want to gain the maximum benefit out of me, they should stay as far away from me as possible, right? So now we have concluded that in one single block, right, in one single color, all the prefix maxima will be first and then the prefix minima. So the only thing that is remaining to solve this problem is what will be the partition point after which you decide to split from maxima to a minima, right? So that is the last segment of the video that we will discuss. So let's have our structure again. So this is the first minima, prefix minima, and suppose then the minima decreases, and then these blue colored elements are the second prefix minima, which will of course be smaller. Then this green colored elements, they are the third prefix minimas, they will also be smaller. Then the fourth set of prefix minima is the yellow colored, they will be smaller. And the last set of prefix minima, they are the smallest ones, right? And we know that in this segment you partition over here, right? You partition over here where you have this as maximas, prefix maximas, and at the end you will have prefix minima, right? But what point should you partition at? So let's assume that that point is a general any partition, and then you have x element inside of it. So if you have x element inside of it, then assume that this size of this block is, let's say, t. I'm using this notation because the editorial also uses this notation. Then if you have x element here, then t minus x element on the right hand side, and assume that the total count of all the elements, because that is the only thing that we care about, right? Sum of all elements of all the blocks, because we know that anything inside this block, anything, right, as long as it's a prefix minima, it will invert with everything, but if it is a prefix maxima, it will invert with nothing at all, right? So suppose this entire length is s, right? So you can see that you have maximas on this block, and we have already concluded that maximas contribute 0. So their contribution is 0. So the only contribution is coming from the minimas, right? And if this is the minima, you know that this minima already inverts with everything over here. But now, since you have changed this block to a maxima, this inverts with this as well. This was the actual benefit. Like, you are now getting contribution from inside your box. So the total contribution will be, you can pick any element on this side and any element on this side, on the left hand side. And that is the reason why we are not looking at the right hand side. You see now that we added an artificial constraint, that in order to focus our attention on one specific thing, an element can only be inverted with elements on the left hand side, right? So if you select any element from here, t minus x, and any element from the left hand side, which will be s plus x, right? This will be the total number of contribution from this entire block, right? And your goal was to maximize the contribution of the entire block and not the individual ones, right? Because once you move out of a block, then this block and this block doesn't really differentiate much, right? You might as well color them in the same color. So this is the thing that you want to maximize. This is the total number of inversions. So now you want to maximize a function which is f of x equal to this, right? So if you expand it, f of x is equal to t into s plus t into x minus s into x plus, sorry, minus x square. And then you can see that it is a quadratic equation, right? And it will be maximum when its derivative is 0, right? So this is a constant. This goes away. Differentiation of this is t, differentiation of this is s, and differentiation of this is 2 into x, right? And then you can see that it will be maximized when 2x is equal to t minus s, or x is equal to t minus s by 2. And even if you did not differentiate, you can clearly draw the graph of a cubic equation with a negative leading coefficient. So it would look something like this, I believe. Yeah, it should look something like this. So you can see that this is the maximum point, and the values will start rapidly decreasing. So if this is t minus s by 2, and if t minus s by 2 is not coming out to be an integer, then look to the left or look to the right, and then you can get the maximum value, right? So now using this, you can figure out where to partition that array, right? And in fact, you have solved this problem, right? That is the entire idea, that now all you have to do is compute the blocks of prefix minimas, like all the same colored elements in that same block. And then when you are going from block to block, you add contribution of each block. And how do you add contribution of each block? You count the number of you count the total number of elements in all the blocks that you have seen so far. You call that as s. Then you call the size of your current block as t, and then you try to partition it at t minus s by 2, and then instead of actually partitioning it, you take this x and you plug it over here. You get this x, and then you add the contribution of that block. So this was the contribution technique of each block, right? And in this way you can solve the problem for any given array A, right? Now there is also a harder version of this problem that appeared in a recent code forces round as the last problem of a div2 round. But that harder problem, right, that is very easy to solve if you have if you have solved till here, right? Because reaching from 0 till here was the most difficult part. Now it's all about optimization on how you want to like answer these queries faster. So in the harder version of the problem, they ask you to solve the same problem but on any given subarray. So in that, if you have understood so far, you can actually go to the editorial of that problem and you can try to solve the remaining part. But even if you don't want to do that, but even if you did get the idea of why this greedy algorithm, the original greedy algorithm did not work, but our gut feeling was correct. See, we did find a case where maxima had to be earlier than minima, right? And in fact, while I told you, right, like I'll tell you how I constructed this counter example. This is by arriving at the correct solution in a sense, and then realizing that this minima blocks that were being created, right, those were important and not just dividing maximas followed by minimas, right? So yeah, this was just one of the case studies that I wanted to do for greedy. Now, of course, like this exact same idea will not be used in future greedy problems, but that's the beauty about it. Like even though the exact same idea will not be used, every time you solve a greedy problem or you are not able to solve it and you find a counter example, you learn some new technique of approaching greedy problems, right? So for example, here we followed our gut feeling, but then it did not lead us to the correct direction. So we started with something that we can prove. And what can we prove? We can prove that the last element will always be a minima. But then we tried to extend the same reasoning to everything, and then we realized our flaw, that the one biggest thing that we are missing is the duplicates. And why were we and when we included that duplicates, we realized that prefix maximas actually contribute nothing. So you will never take them unless you want to do some optimizations for unless you want to do some planning for all the other elements to get some more contribution from your block. So that's it for the video. Let me know in the comment section if you found this video useful, and if you would like more type of videos where on this topic, not necessarily on this topic, but on this theme, where we just take a problem, dissect it, discuss about it. We don't care about the implementation detail, right? I don't care about whether you are able to implement this problem using like splitting it into blocks of minimas or not. Even if you don't do that, but if you at least got the idea of why all of these blocks, things, etc. working, and now if you go and read the editorial, I hope you will now be able to understand what the editorial is saying much better. So yeah, let me know in the comment section, and thank you.